Hello folks, welcome back to video number 2 of our series. Yesterday we talked about, or last video we talked about arithmetic series. Today we're going to talk about geometric series, and then in the third video we're going to talk about series that go on to infinity. So let's get started. Much like an arithmetic series, a geometric series is simply the sum of the first n terms in a geometric sequence. So a quick reminder, an arithmetic series is a series that has a common difference, something like 2 plus 5 plus 8 plus 11, where each term in the series goes up by some common difference. In this case, the difference would be 3. A geometric series, again, is a series of additions, but instead of jumping up by a common difference, they go up by or down, I suppose, by a common ratio. So, for example, 2 times 2 is 4, times 2 is 8, times 2 is 16, and so on and so on. Now, it's kind of interesting. So, geometric series, we have touched on a little bit the fact that an arithmetic series can be described as a not an arithmetic series. An arithmetic sequence can be described as a linear relationship where it has some common slope where it goes up the same amount each time. A geometric series can be described as an exponential relation, which is kind of relevant to what we're seeing right now. You hear a lot of people describing the spread of a pandemic as an exponential growth, so it is relevant to what we're seeing. I do have a little story here that I want to share with you guys, just an interesting tale from I believe Indian culture. So it is exponential growth and the legend of Pal-Pesam. And excuse my pronunciation. Exponential growth is an immensely powerful concept. To help us grasp it better, let us use an ancient Indian chess legend as an example. So the legend goes that the tradition of serving Pal-Pesam to visiting pilgrims started after a game of chess between the local king and the Lord Krishna himself. The king was a big chess enthusiast and had the habit of challenging wise visitors to a game of chess. One day, a traveling sage was challenged by the king. To motivate his opponent, the king offered any reward that the sage could name. The sage modestly asked for just a few grains of rice in the following manner. I think the key word here is a few. The king was to put a single grain of rice on the first chess square and double it on every consequent square. So if anyone here plays a bit of chess, you would know that our chessboard is an 8 by 8 board, meaning that there are a total of 64 squares on a chessboard. So they're saying put 1 on the first square, and then 2 on the next, and then double that, and double it, and so on, until you've doubled it 64 times. So just stop and think about that for a second. Right away, it seems like, okay, well, 1 double is 2, and then 4. It doesn't seem like much, but as soon as you start thinking about this exponential growth and how quickly things grow when we start thinking about them exponentially, or start thinking about them in terms of a geometric sequence, what we end up finding is that to figure out the total amount of rice on this board would be 2 to the power 63, plus 2 to the power 62, plus 2 to the power 61. And it's just a massive, massive, massive amount of rice. The number of grains of rice, I think, is something like enough to fill India a kilometer high, or something ludicrous like that. It is an unimaginable amount of rice. So you can see that these geometric series, or these geometric sequences, grow really, really quickly. So I would never expect anyone to sit there with their calculator and actually do this. Type in 1 plus 2 plus 4 plus 8 plus so on and so on and so on and so on. So there has to be an easier way, and that's what we're going to talk about today. So also, like arithmetic series, it would be time consuming to calculate this without a formula. So that's the plan for today. We're going to talk about that formula, and we're going to take a look at a couple of examples. So geometric series continued. You've just seen a new band. You text the link of the band's website to 5 friends. They each forward the link to 5 friends, and so on and so on. So we're going to take a look at how we would solve something like this with a case that's a little bit easier than 64. So the number of people receiving the link can be modeled by a geometric series where the first term is 5, the 5 links that you sent out originally. And then the common ratio is also 5 because they're setting it to 5, and then they're setting it to 5, and so on. If we wanted to look at the first 4 terms in the series, we'd have this right here, where there's the first 5 links you sent out, there's the 5 links they sent out, there's the 5 links they sent out, and there's the 5 links those final people sent out. Now, we would think of this as a series because just because these 5 people sent out links, so that's 25 new people that we're adding to the total number of people that have seen this band. And then they would send out 5 links, so there's 125, again, new people, so additional people. So we want to add each term in the series instead of thinking about it like a sequence. So let's think about this situation for a second, and let's see if we can't solve it. Instead of adding up all the terms, let's think about it in maybe a little bit roundabout of a way, but you'll see why here in a second. So to develop a formula for the above series, consider the following. So if we take the original series and we list it, so there's our equation 1. We're going to label this series equation 1, where we have 5 plus 25 plus 125 plus 625. Okay, we're then going to take that first equation and multiply it by the common ratio. So we're going to take this equation here and multiply everything by 5. And what we're going to notice is that we take this 5 and we multiply it by 5, it turns into 25. And this 25 turns into 125, and this 125 turns into 625, and so on and so on. So each of these terms in our series just becomes the next one. So we have 5 times our series containing 4 terms turns into this thing, which we will label series number 2, or equation number 2. Then what I want to do is subtract equation 1 from equation 2. We're going to take this new equation 2 that we have, and from it we're going to subtract the original equation. And what we're going to find is because this new equation just turned into everything from the original equation one step forward, that the 25 from our original equation is going to cancel out with the 25 from our new one, and the 125 will do the same thing, the 625 will do the same thing. So then what we're left with is 5 minus 1 of our series is equal to negative 5 plus 0 plus 0 plus 0 plus 0 plus 3,125. And when we add those up and divide by 4, we get our 780, which we already know is the answer for this question. Now, again, this might seem like a little bit of a roundabout way of looking at this, but what we can do now is take this example and put it in the general case. So a geometric series can be expressed as this. And that's not just true for geometric series. This statement is true for all series, where a series is expressed as term 1 plus term 2 plus term 3 plus term 4 plus all the way up to term n. So if we do the same steps for the general case that we just did for our previous example, right? So what we can do is we can take this and rewrite it as our definition of a geometric series, right? So term 1 plus, so term 2 is just term 1 times r. And then term 3 is term 1 times r squared, and then term 4 would be term 3 times r, so term 1 times r cubed, and so on until we get to term 1 times r to the n minus 1. So if we follow these same steps, if we take our equation 1 and we multiply it by the common ratio, what that's going to do is it's going to take this term 1 and turn it into term 2, and take term 2 and turn it into our term 3, and so on and so on and so on, until we get something that looks like this. So this is our equation 2. Now again, just like with the previous example, let's take equation 1 and subtract it from equation 2. And what we'll see happen here is that this term will cancel out with this one, and I'll even color code it here so we can see it. So this term will cancel out with that one, and this term will cancel out with that one, and so on and so on and so on. Right, this term here will cancel out with one of the terms in there, and finally, once we start canceling out all the terms at the very, very end, right, something in here will end up canceling out with that one, and what we'll be left with is a bunch of zeros, negative term 1, and term 1 times r to the n. So now if I take my equation and I solve it for the sum, the series, by adding these two together, right, dividing both sides by r minus 1, what I end up with, this nice formula here that only contains term 1, r to the n, and r, right? Or if we know other information, because sometimes it'll be different information we're provided with, we could take this equation and rewrite it a little bit by turning it into this one as well, where we know that t1 times r to the n is the term after the last one in our series, so we could rewrite that as the last term times r, right? If we expanded this bracket here, we would get this one here, where s is the sum of our series, right? T1 is the first term of our series, r is the common ratio, and n is the number of terms, right? Or here, if we didn't know the number of terms, we could do something like this, where we did, again, r times tn minus t1 all over r minus 1. Okay, so let's take a look at our new formula in action. So, for example, if I wanted to find the first term of a series, what I would need to do is take my new formula, so my Sn equaling term 1 times, what am I doing here? R to the n minus 1. All over r minus 1. Whew, I'm having an off day today. R minus 1, right? So then now we're going to take the information that I know here and we're going to solve for t1. So what do I know? I know my Sn here is 13,116. I don't know my t1 because that's what I'm trying to solve for. I know r is 3 and I know n is 7, right? It's this one right there. Minus 1 all over 7 minus 1. So now it's just a matter of simplifying and solving. So if I take my 13,116 and we will multiply it by 6, right, to get this to the other side, is equal to term 1 times, grab my calculator here, 3 to the power 7, 2187 minus 1. So 2187 minus 1 is 2186. I suppose I could do that in one step. And then divide both sides by 2186. So 13,116 times 6 divided by 2186 is 36. Okay, so again, it's all, when we have a series, the nice thing about these types of questions is we have a formula, right? So once you know the formula and you know all but one of the missing values in your formula, it's just a matter of plugging the numbers in and solving for what you're missing. Okay, so let's try another one. So at any point in time, feel free to pause the video, try the question yourself, and then come back or restart it when you're ready to see the answer. Okay, so here's the next one. So if we take a look here, we're looking for the series, or the sum of the series of 8 terms, where my first term is 5. Oh, excuse me. My r value is 2. Contains 8 terms. Okay, so then 5 times 2 to the 8 is 100. Nope, sorry. So, having an off day here. 256 minus 1. 2 minus 1 is 1. So 5 times 255 is 1,275. Okay, part B. So again, feel free to stop the video whenever you'd like. Part B, the pieces of my series here aren't explicitly stated, but we can infer them from the information given, right? So T1, term 1 here, is 12. My common ratio here, if we take term 2 and we divide it by term 1, we'll see is -1/2. And the number of terms is being provided right there. N is 11. So now we're going to take the sum of the first 11 terms of the series where we have 12 is term 1, and then my common ratio here is negative 1/2, right, to the power n, which is 11, minus 1, all over r, which is negative 1/2, minus 1. Right, so again, plug that into our calculator, do some quick calculations here. So we get 12 times 1 over 2048 minus 1. Sorry, negative 1 over 2048 minus 1. All over negative 3 over 2. Okay. And then we would do some calculations here. So if we simplified this a little bit, so if we multiply the negative 3 over 2 to the top, we would get negative 8 times inside the bracket here. So this is 2048 over 2048. So negative 9 over 2048. And then simplify our fraction here, and we get $256 over 20. Sorry. Having a really off day, I guess. 2049 over 256. Okay. If you have a decimal there, right, 2049 divided by 256 is 8.00390,625. Really messy decimal, so I would rather see it as this fraction here. Yeah, so let's take a look at another one. Just try a couple of these examples, right, and we'll cut this video off a little shorter. Like I said, I'll have another video up either today or tomorrow about series that go on to infinity. I'll post the assignments to this section on Teams. Make sure to give it a try before our Q&A Wednesday. And I'll give you guys some time into next week too. I think what I'll do is I'll end up posting either like a quiz or a little mini test. Just remember, it's not going to be 4 marks, just to kind of see how we're making out. Alright, so if we have this series here, calculate the number of terms in the series. So in this case, we're looking for n, where we know the first term is 5 over 4. We know the common ratio is what? So if we take 5 over 6 and we divide it by 5 over 4, we get 4 over 6, which is 2 over 3. We know that the t-nth, sorry, not the t-nth term, my mistake. We know that the sum of our n terms is going to be equal to 3.7066. So now it's just a matter of solving for n. So if we take my equation, 3.7066 is equal to 5 over 4 times 2 over 3 to the power n, all minus 1, all over 2 over 3 minus 1. Okay, so now I need to try and solve for n here. So what we're going to do is we're going to take this equation here and start expanding it in order to get this term here that has a power of n by itself. So if I expand the bracket, I get 5 over 4 times 2 over 3 to the power n minus 5 over 4 all over 2 over 3 minus 3 over 3 is negative 1 over 3. Okay, then I'm going to take everything that does not contain this variable and try to move it all to the other side. So if I take my 3.7066 and I divide it by 3, negative 3, sorry, I get negative 1.23553, that thing repeating. If I take this and I move it over to this side, so to that I add my 5 over 4, and then I'm left with 5 over 4 times 2 over 3 to the power n. Right? Take the negative this thing and add 5 over 4 to it. And then I'll take that answer and divide it by 5 over 4. So what I get is 2 over 3 to the power n is equal to 0.01157 repeating, which is a messy number to solve for, but what that means now is I have to take this thing and use some logarithms, right? So n times the log of 2 over 3 is going to be equal to the log of 0.011573 repeating. So then n is going to be equal to the log of 0.011573 repeating divided by the log of 2 over 3. So when I plug that into my calculator, so the log of this number divided by the log of 2 over 3 is approximately 11. So what that means is there are approximately 11 terms. If you were to take that number and round it off, I'm assuming what probably happened here is when this question was made, this would have been maybe 6 repeating, right? It would have been 3.7066666 repeating or something like that. But because we cut off a couple of decimal places here, our number isn't exactly 11, but it's close enough. It's like 10.997 that we can assume that there were 11 terms in this series. Okay? All right. 2 more examples, and then we'll call it a day. Again, whenever you guys want to pause the video, try some of these by yourself. You're welcome to. If you're not confident yet, keep watching the examples. Maybe after you've seen them done, go away, come back, try them again. And again, what I'll do is I'll kind of grab some questions from the textbook, and I'll put those on here as well. All right, so determine the sum of each of these series. So in this one, the n is unknown. So in this case, it might be worthwhile to use this formula right here, right? Our r times t to the nth term minus the first term over r minus 1. So the sum here is going to be r times the nth term minus the first term over r minus 1, right? So what we're going to do is we're going to use this formula to help us solve these questions. Okay, so that means the sum of my n terms is going to be r. So r in this case is 1 over 16 divided by 1 over 64. So it's equal to 4. T1 is 1 over 64. And Tn is 1024. So let's do that. R is 4. Tn is 1024. Term 1 is 1 over 64. And again, R was 4. So solve these. 96 minus 1 over 64 all over 3. So this is 262,143 over 64. And if we combine our denominators, we get 192. Now, it might seem like a bit of an ugly number here, but if we think about this for a second, right, 1 over 64 plus 1 over 16 plus 1 over 4 is where we're getting this kind of nasty decimal from, because then the next numbers are going to be 4, and then 16, and then 64, and so on and so on and so on, right? So the rest of these numbers are going to give us a nice, neat whole number answer, but because of these first three fractions, it kind of gives us this weird fraction here. All right, let's do one more here, and then we'll take a look at one of these questions with a sigma notation and how you would write a geometric series with a sigma notation, and then we'll call it a day. So again, here we have term 1 is -2, r is also -2, term n is -8192. So if we're looking for the sum here, the sum of our n terms is going to be equal to r times Tn minus term 1 all over r minus 1. So -2 minus 1. So we get -2 times -8192, 16,384 plus 2 over -3. And our final answer here is -5,462. And again, our answer makes sense here because if you take a look at the numbers in our series, all of these are whole numbers. Now, right away you might say, well, wait a second, like how is this number not like more than that? Well, not more, like the absolute value not greater than this one, right? We're adding stuff up, but see what ends up happening here is because of the negative r value, the sum of these two terms is 2. And then the sum of these two terms is going to be 8. And the sum of each term going forward ends up being a positive number, so it would make sense that when we're doing that, this final term here at the end and then a bunch of positive numbers actually gives me a number whose absolute value is less than my Tn, which is kind of an interesting thing that happens there. Okay, finally, our sigma notation. So in this case, we have to be really careful because sigma notation doesn't care about term number, right? Your sigma notation doesn't care if it's term 1, term 2, term 3, right? What it'll do is it'll take whatever this lower limit is and throw it in here for k. Whether that gives us something that's a 1 or a 2 or a 3, right? It doesn't care. So we have to be able to kind of translate sigma notation into the T1 and the N and things like that, right? So what I would suggest for a question like this would be to actually take these values and plug them in. So 4 times 2 to the 3 minus 1 plus 4 times 2 to the 3, sorry, that's 4, my mistake, to the 4 minus 1. And then 5, and then 6, and then 7, dot, 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 and finally 4 times 2 to the 10 minus 1. And the reason I say to do this is because a lot of students will mistakenly kind of assume, oh, okay, well, we're going all the way up to 10, so that means n is going to be 10, right? And you have to be careful because that is not the case. Also, students might mistakenly say, okay, well, if I'm starting at 3 and I'm going up to 10, that means n is 7. And again, n is not 7, right? So we really have to be careful about that. If term 1 has a 3 here, and term 2 has a 4 here, and term what 3 would have a 5, and 6 would have whatever, right? So you have to be careful. So what that means is that this value here is actually term 8 in my series. So we really have to be careful about that. So now, if I simplify this a little bit, so 3 minus 1 is 2, 2 to the 2 is 4, and 4 times 4 is 16, and then plus, and I'm actually just going to skip the rest of it, because we only really care about Tn if we're trying to find the sum here, right? So 10 minus 1 is 9, and 2 to the 9 is 512, and 512 times 4 is 2048. Now you could have simplified this a little bit, right? This is 2 to the 2, and you could have combined them, right? 2 to the 2 times 2 to the n minus 1, and simplified it a little bit more if you'd want. But again, we're just looking for the sum, so not necessary unless it states otherwise. So now, if I'm trying to find the sum of the first 8 terms of this series, now it's just a matter of saying, okay, well, this is going to be 16 times. What is my r value here? Right? What's happening from term to term? And this might be where it would be beneficial to take a look at this and say, to actually do this second term. But again, remember that we can kind of translate geometric series to exponential growth, where in the same way that in arithmetic series, the common difference was your slope, in geometric series, the common ratio is going to be this base value of your exponent. So in this case, the r is 2, right? So it's going to be 2 to the 8 minus 1 all over 2 minus 1. Okay, so now it's just a matter of solving. So 2 to the 8 minus 1 times 16, which is 4,080. Okay, so that is it for today's work. Again, what I'll do is I might post a couple of questions to go along with this video, and I will put the assignment for this unit up on Teams. I don't necessarily expect you guys to be finished the assignment by the time we have our Q&A, just to have a look at it, and maybe what we'll do is we'll talk about it a bit more next week. I might also put a quiz up at some point in time, but we'll talk about that before I make it available. And what I'll do is I'll give a date and a time for the quiz when I post it. That way you'll know well in advance when it will actually be. All right, so this is it for today. Have a great day, and I'll be talking to you guys soon.